Have you wondered if all wind turbines spin the same direction? You and I have an insatiable appetite for electricity. Come with me and we'll look at the issues relative to wind farms and the communities that they serve. This is the Windfarm Guy. Hi, this is Dennis Stout, and thank you for joining me for this episode of the Windfarm Guy. A rose by any other name is still a rose. And if a clock rotated the other direction, a minute would still be a minute. But doesn't matter what direction wind turbines turn. Turns out it actually does. A study recently done by the German Aerospace Center suggests that it may actually make a difference. Almost all wind turbines in the world today turn clockwise. Although that may have been a random decision back in the day, it may really make a difference today. In fact, in the Northern Hemisphere, which is where 96% of all installed wind turbines are located, that common clockwise rotation may not be best. According to their findings, for a single turbine, it doesn't matter at all what direction it spins. However, wind turbines are usually placed in groups, a wind farm, so there are effects on downwind turbines. They have built a computer model that simulates the airflow across a wind turbine spinning in either direction and then calculates its effects on a downwind turbine. Interestingly, they concluded that it makes no difference at all during the day. However, at night, it makes a big difference. And if the first turbine spun counterclockwise, then the power output of the downwind machine increased by 23%. That's huge! There are several factors that together cause this effect. First, there's wind shear. That is when wind blows differently at different elevations. This takes place in the first few hundred meters above the ground, an area known as the boundary layer. This wind shear is a concern for wind companies. Not only does it make the turbine less efficient, but because the rotor is hit with a different wind, both speed and direction, at different places in its rotation, it also causes more wear and tear on the machine. During the day, the sun heats the ground, which heats the surrounding air, which rises in turbulent swirls, resulting in a well-mixed boundary layer that acts the same way all the way up. As a result, the entire rotor assembly is typically hit with a fairly consistent wind. However, nighttime is a different matter. At night, the ground cools, and that swirling motion tends to go away, or is at least reduced, and the boundary layer stops mixing as well. From the friction from the ground, which is enhanced by the drag of buildings and vegetation and such, the wind close to the ground moves more slowly than the air higher up. This is referred to as altitude-related wind shear. Because of the lack of swirling updrafts, this effect is more pronounced at night. Believe it or not, the Earth's rotation even comes into play here, and the moving air is pushed slightly to the right in the Northern Hemisphere and to the left in the Southern Hemisphere. It's a phenomenon known as the Coriolis force, and the faster the airflow, the greater that force. Therefore, the night wind has a gradual change in direction relative to the elevation above the ground. Given the size of today's larger turbines, the sweep of the rotor is big enough to actually be affected by this, especially in areas of great wind, which is where wind farms are typically sited. Okay, so the Coriolis force accounts for this weird wind that might hit a wind farm, but how does that affect a downwind turbine and its energy output? Well, it's simple. When the wind hits a turbine rotor, it pushes the blade in one direction, then diverts in the other. In other words, if the wind pushes a conventional rotor, it will be in the clockwise direction. The wake or diverted wind would be moving in a counterclockwise direction. In the Northern Hemisphere, this counterclockwise wake is in conflict with the Coriolis-induced turning of the undisturbed adjacent wind. thereby hampering the wake's ability to pick up energy from the undisturbed adjacent wind before it hits the downwind turbine. As a result, the downwind turbine is less efficient. However, if that first turbine rotated in a counterclockwise direction, then its wake would be clockwise, matching the Coriolis-affected adjacent wind. The two would combine and hit the downwind turbine with more force, making it much more efficient. Keep in mind, this scenario is in the northern hemisphere where Coriolis negatively affects turbine efficiency. Turbines in the southern hemisphere already are taking advantage of this Coriolis force. Kind of crazy, isn't it? If you like the things I've said today, be sure and click like and subscribe below. Leave a comment or ask a question if you like as well. The bottom line is we are learning that turbines can be as much as 23% more productive in the northern hemisphere, which is again where 96% of turbines are located, if they would just turn the other direction. But the blades are designed to spin in one direction. To change that would require retooling factories and replacing hundreds of thousands of blades. At this point, would that massive added expense be offset by the increased efficiency? We're not sure, but it sure might be worth more investigation. This is Dennis Stout, and I'm the Windfarm Guy. Thank you for watching. Working together, we can make good energy decisions and save our planet. I am the Windfarm Guy.